Assalamualaikum, my name is Nazika Bashabita Halim, and today we will present to you about heat transfer analysis of a flat plate solar water heating system. This is our team member, which is Alia, Hazika, Aina, Patricia and Amni.
Assalamualaikum warahmatullahi wabarakatuh. My name is Aina Sofia and I'll be presenting the design of our solar water heating system. The diagram shows that the collector is structured with several key components. First, the glazing sheet is made of glass, which allows sunlight to enter while minimizing heat loss. Beneath that, we use a copper flat plate. It absorbs solar radiation and transfers the heat to working fluids. For insulation, we use fiberglass, which minimizes heat loss from the back and side of the collector. Lastly, the entire unit is enclosed in an aluminium outer casing which is both lightweight and provides structural protections. The dimensions are detailed in the diagram, with the collector measuring 1600 mm by 1000 mm and a total thickness of around 140 mm.
Hi, my name is Patricia. I will explain about simulation setup. For this simulation, we begin by designing the geometry of a flat rectangular plate with one indent and two outlets. This setup represents a typical heat transfer surface. Once the geometry was complete, we generated a mesh to divide the domain into small elements for accurate numerical analysis. This simulation uses copper and aluminum as a solid material. You can see the key material properties on the right, including density, specific heat, and thermal conductivity. A constant heat flux of 800 watts per square meter was applied. At the inlet, we assigned copper with an initial temperature of 298.15 Kelvin, while both outlets were set to a higher temperature of 473 Kelvin, simulating heat flow through the materials. This setup helps us study how heat is transferred from the heated plate to the fluid flowing over it.
Hi, my name is Nadia Samipasmadi. I want to explain about simulation result. This graph shows the result from the CFD simulation, which help us to understanding how close the solution is to being accurate. Results are like the remaining error in the calculation after each step or iteration. At the start, the results are held to but will decrease over the time. This means the simulation is improving. Each line represents different variables, mass as velocity, energy, turbulence. The purple line, which represents energy, is the most noticeable and shows a steady drop. However, since the values are still quite high, it indicates that the simulation have not fully coverage yet. So some adjustment like refining the mesh or reducing the step might be needed. Thank you.
Hi, my name is Amni Alimah and I will present about theoretical calculation and simulation calculation. For the theoretical, first we need to know H and K by using forced convection. Okay, so after that we can get first we get a T film and we get the Reynolds number, Nusselt number. So from that we can get the K value and H value. Okay, so for the convection, heat we get is 812.442 watt. For the heat conduction we get 65.25 watt. For the simulation calculation, for the conduction we use the same K, but the result we got 474.57, and then for the convection we get 812.42 watt. That's all.
My name is Nazika Marsha bin Talim and I will talk about the comparison and analysis. In our comparison convention, results showed good agreement between theoretical and simulation methods. However, conduction values were significantly higher in the simulation. This is because theoretical calculations are based on ideal assumptions such as steady state, one-dimensional heat transfer, and constant material properties. In contrast, the simulation provides a more realistic analysis by considering multidimensional heat flow, varying temperature gradients, and changes in material properties like thermal conductivity with temperature. Additionally, numerical approximations from meshing and element divisions in the simulation can also affect the results. These combined factors explain the discrepancies observed in conduction heat transfer. For conclusion, in this project, we analysed a flat plate solar water heating system using theory and ANSYS Fluent simulation. We studied conduction, convection, and radiation. The convection results match well, but conduction differed because theory used simple assumptions while the simulation was more realistic. The system is efficient and practical for using solar energy. Future improvements can be made by refining the simulation and using better materials. Overall, this project helped us understand heat transfer better and showed the value of simulation tools.